Hello everyone. Welcome back to Deep Learning video lecture series. This is Dr. Chiranjeevi Manike, Professor in Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. A previous video, I explained a theory concept related to the hyperparameter tuning. And in this lecture, I'm going to explain like a hands-on session mainly, how we can build this multi-layer perceptron, and for an example like a classification problem, and how our input would be, and then what are the different layers in the hidden layers, and what are the activation functions, and we will also discuss how we can do this hyperparameter tuning, that is by adding this batch normalization and the dropout mechanism. So first in this lecture, I just mainly divided into the two parts. This is again divided into two parts. The first part, I am going to explain about the theory concept, like mainly what is this MNIST data set, that is modified National Institute of Standards and Technologies. That is a full form of MNIST. And what is this data set? And then second, next we'll see the MLP architecture, like how many, what are the different layers and what is the input and output of each layer, and that we will be explained. And the second part is a hands-on session, that is training an MLP multi-layer perceptron for a handwritten digit classification problem, and this is mainly useful for the students and also the researchers who want to begin their career, the research in this deep learning. So they have to understand the theoretical concept, and that is like suppose batch normalization, dropout mechanisms. They have to understand the mathematics behind, and then the second part is using that techniques and to understand clearly, so they can apply on the real-time data set or any synthetic data sets. So let us first see what is this MNIST data set. As I said, the full form of this MNIST is a modified National Institute of Standards and Technology. So this data set consists of 70,000 handwritten digit images. So each image is size 28 by 28 pixels. So here, and this is a simple images, like here you can see the each digit is an image. So sample images from this MNIST test data set. We have digits like 0, 1, 2, 3, 4, like 0 to 9. So there are some set of images from this test data set. So this data set we are going to use, I'm going to use mainly to explain this multi-layer perceptron, and the main objective is to understand how we can apply how we can use this or fine tune this hyperparameters. So here you can see these are all the grayscale images. Like if you look at this, each image, like each digit is a image of size 28 by 28. That is a size of image, each image. Like suppose if you take this image and its size is a 28 by 28 pixels. So it's a grayscale image. The values are ranges from 0 to 255. So here you can see, and the values like the 0 and 0, what is the value, the grayscale value represents, like black color. You can see from this image and also from this image, you can see there are different, like some gray color, white, and dark black color, like that. So each is going to have a grayscale value. So if you look at this image, and you can see, and say it's a 28 by 28 pixels. So, and you can see this is outside of this part, and like suppose this is the region outside the region, in this region. So this region, all the values are 0. So that means, so 0 here white and 255 means black. Okay, so the values are within the range from 0 to 255. So here you can see, you can just search any image and you will get the detailed complete details of how an image would be represented as a grayscale image. And like suppose if there are, if the size is, the dimension is 28 by 28 pixels. So this is one image that we are going to use in this MNIST handwritten digit data set. And like another, like color, if you take a color images, so here this is a original image, and color is images means each pixel value is a combination of 3 channels like red, green, RGB, red, green and blue. Like here you can see, so each, like red, there is a separate channel for each color. So blue, green and red, there are 3 channels, but in the grayscale image only 1 channel. But we are not going to currently work on this color images, so we will be going to work on this grayscale image. So the values, pixel values, intensity values are, which are ranges from 0 to 255. So now we have to understand the architecture mainly. That is the input that we are going to give, we are going to build a model, that is a classification model, to recognize the digit, handwritten digit. Okay, like suppose if you have written 0 or 1, 2, 3, 4, like 0 to 9, and if you supply that image that is in the form of 28 by 28 pixel image as a grayscale image to this model, that model has to predict whether the handwritten digit is correct. Has to predict the handwritten digit. So like here you can see what is a basic multi-layer perceptron architecture to perform this task. So we have to understand mainly what are the input layers, why these many neurons. Like suppose here you can see there are 784 neurons in this input layer, and the hidden layer we have 64 neurons, and the output layer there are 10 neurons, that is from 0 to 9. So now first we need to understand, because these are mainly depends on the input, and this is mainly depends on the output, what kind of a problem you are going to, what kind of a task you are going to solve by using this deep learning model. So the output layer, number of neurons in the output layer will mostly depends on this, the problem that the task you are going to do it. So here input layer also, input layer mainly, like why we need to have 784 neurons in the input layer, and why this hidden layer 64 neurons. But these are almost like depends on the input, whatever the image, what is the size of image. Like suppose 28 by 28 is the each image size, each image dimension, or the size in MNIST handwritten digit data set, any image in that data set, and that's the dimension is 28 by 28. So 28 by 28, that means, so 28 times 28, that is 784 total values, pixel values. So if you go back and you can see here these are 28 by 28, so there are 784 pixels in that image. So for each pixel we need to have a neuron, so that's why input layer should have 784, that is 28 by 28, total 784 neurons to process 784 neuron. That means for each pixel there should be one neuron. So that's why here the 784 neurons in this input layer. Next, hidden layer, and this is we have to decide like how complex the model you want, right? If you want more complex model, and the more hidden layers and more in each layer more number of neurons. That means I think if you look at this one, this is an image which is obtained from the internet. The problem that we are going to solve and the network, complete a network architecture for that problem. So here you can see the sample image that we are going to give as the input to this one is a digit 6. Here you can see that its size is 28 by 28, and then here you can see the input layer is going to have 784 input pixels. So there's 784 neurons and 128. In this hidden layer, we have the two hidden layers. That is one layer with 128 neurons and another layer with 64 neurons. And then the output layer is having the 10 neurons, because we have to classify whether the given digit is either 0 or 1 or 2 or 3, right? Anything that is in between 0 and 9. So that's why, so we need to have the 10 neurons in this output layer. So let us do some little bit calculation part also. Like suppose if you take this image, and what is the input layer? Like suppose there are 4 layers. This is input layer, and this is these two are the hidden layers, and this is output layer. And what will be the size or the input size, and what output it will be produced. So suppose if you take this one, and this is a 784 input, and this here we are not going to do anything. So this is only to supply this pixel values. And if you look at this 128 neurons, so 128 neurons and this 784 and the respective weights and plus bias will be given, so that its total 784 pixels will be given as input to this, and it will produce the 128, because in this layer 128 neurons, so each neuron will produce an output. So the total the output is 128, and then this input will be given to this layer, another hidden layer. So and for input to this is 128, so that is 128, that is one dimension array, and the output produced by this is a 64. Okay, this is output, and for this output layer 64 input will be given, right? These are the 64 values, and it will produce the 10 output values. So then, and we will classify, so whether the given digit is either 0, 1, 2 or anything in between 0 and 9. So this is about architecture, that is to classify the given handwritten digit is belongs to either 0, 1 or 2, like. So now, so in this case, one more we need to discuss. So here we have to use the different activation functions, like the previous videos I have already explained the standard activation functions like relu, sigmoid, softmax, tanh, etc. So again, like which activation function will be used, that need to be understood, why we are using this activation function. Okay, why we need to use this tanh or relu or any other activation function. So that is a basic knowledge you need to have before we start any experiments. That is like if you want to do any research, so first we have to build a strong foundation. So as part of that, we have to understand each and everything. Okay, so what are the different and why we need to use, like suppose here in this hidden layers, in this example we are going to use a relu as a activation layer, and for the output layer we are going to use a softmax. So why we need to use this in hidden layers relu, and why we use the output layer softmax, so that you need to understand, because this I have already explained. I think it's a simply wastage of time. So I request you to go back to the previous videos, and if you have any queries. So let us see that coding part. It's very simple. So this is Colab notebook, And before you start running the code, you have to ensure that whether it is connected to the computing engine or not. You can see here this is connected. You can see the tick mark. Now let us see the step by one how that whatever the multi-layer perceptron we discussed, the architecture, how that can be implemented. So before the first step, we need to do like a data preparation process, that is, and also we have to import the TensorFlow, and also from the TensorFlow we have to import the Keras, and another the basic library, that is NumPy, also need to be imported. So then, and the next part is loading the MNIST data set. So here we have to load whatever the data set we are going to work is a MNIST handwritten digit data set, which has 70,000 images of 28 by 28 size. So that data set need to be loaded. So here you can see this is a data set which is available in the Keras datasets dot MNIST. With this function we can load this MNIST data set. And then this next part is normalizing the data, that is to make the training faster and stable, and we have to normalize the data. So here, like suppose in this case we are also doing the reshaping, that is to infer the like dimensions automatically based on the previous layers, etc. But here in this normalization part we are going to convert into the float 32, that is the type, and also like 32-bit integer, each value would be represented as a 32-bit. So, and that would be divided by 255.0. So then the 0 to 255 values, the values within the range in the grayscale image, are converted or transformed into the 0 and 1. So for that purpose we have to normalize the data. So once we run this code, and we will be, I think the data set will be loaded, and also all the required libraries and packages will be imported. So it is taking a little bit time. And go to the next part. Here you can see here, so downloading the data from this, and it has downloaded the whatever the data set we require. Next, building the model. So we have to build a model. Like this is a simple model. So we have used the 128 like first hidden layer, and we used the activation function as a ReLU, and the input shape, that first layer we have to specify the input shape, and the next and subsequent layer will automatically infer the shapes. So that is based on the previous layers. So here we are going to use all the 10 dense layers from the Keras layers, and in hidden layer we used both the hidden layers we used ReLU activation function. So ReLU activation function produces the output if the input is a positive, and the same will be given as output, and if it is 0 or less than 0, negative, and it will produce the output as a 0. So, and I have already explained the advantages and disadvantages with this ReLU activation function. What are the ranges, and how it is correlated with the overfitting, etc. How it solve the issue of overfitting, etc. So I strongly recommend you to go back to the previous videos, and so then you'll understand this. So this is building the model, and the output layer like a 10 neurons, because to classify the 10 digits 0 to 9. So activation function, that is a softmax, because softmax produce output values that is in the range from 0 to 1. So that is the probabilities we can take, because the total probability is equal to 1. So, and this is the model we can configure. So once the model is configured, and then you can compile it. So here we can compile it. We have to specify the optimizer. It's the most frequently used optimizer, add-on optimizer, and the loss, that is to, like, this is mainly like there are 3 parameters we need to understand in this model.compile, like optimizer, loss, and the metrics. So optimizer is mainly to like uh, how to update this weights. That is mainly right. With a optimizer helps us to update the weights, and then loss function, because our objective is to minimize the loss. So, and for the classification problems, we will use this sparse categorical cross entropy loss function, and then metrics, that is to measure the accuracy of our model. So we have to choose accuracy. So that's build the model and then compile it. Next, training the model. So we have to train the model. I think in the previous one video, I have already explained like multi-layer perceptron. This is simply a repetition, but at the end we will see the how we can apply this dropout and how we can change this learning rates and also the batch normalization. That's part of hyperparameter tuning. So here you can train the model, that is, so it will capture the patterns, the relationship, the patterns among the data, right? Underlying patterns or relationship among the data. So here we have set the epochs, number of epochs are 10 and validation split is 0.1. So once I click this, and it will take a little time, it will depends on the speed, but because it's a simple data set, it's so because all the values, we normalize the values from 0 to 55 to 01 only, so it may not take much time. You can see here each epoch already takes here first epoch 9 seconds to complete, and second 10 seconds, like it will be completed. Okay, next, evaluating the model. So we have to evaluate the model. That is, means once we train the model, then we have to check on the test data set. So we have to supply this test data set, that is a features, and this is a target label of that each feature, so that then we can check whether it is matching, how many matches are, etc. Like so, like that we can measure that is evaluate the model and print the result. Like test accuracy, you can see 97.35 percentage. So it is going to the last epoch. Okay, so next, making predictions. So once we tested, that's okay, then, and we'll go for predicting. So we can supply the new sample or unseen data, so that we can verify the accuracy of our model. So in this, let me evaluate this model. So 97.75 has given now. Next, making predictions. If you run this, and we are going to give a digit, and the model will predict, will classify that digit as either 0, 1, 2, or, so that you can see here. And this is the digit location digit we are going to supply here. It's not like it's just location, right? It's a location in the predictions, and by taking the R max value, so in that location the value, right, the digit represents a 6. Okay, so we can cross check that one. Next part is the main part is hyperparameter tuning, mainly the hyperparameter, also called as hyperparameter optimization. And this is a complete code and lit modification, because the parameter tuning need to be done. And this is same as what we discussed so far, and all this part is same. This I kept in a single shell. So here you can see the difference between the previous one, that is without any hyperparameters. But in this model you can see the same model, just we have added in between the layers. Like here you can see one layer is added, like Keras layers, batch normalization. And next we have also added the dropout. So where the dropout is 0.2, that means 20% of neurons will be randomly dropped. Next layer, dense layer with 64 neurons, and activation function is ReLU. And then again, in between this dense hidden layer and the output layer, we have added this batch normalization and the dropout layers with the same rate of 0.2. So this is the change we made. Okay, here nothing else, because only if you look at this code, it is very simply 2 lines only. Okay, adding batch normalization or mentioning the dropout rate, that is 0.2 like this. But we to being a researcher, if you want to do more research and to understand how the model accuracy, how the batch normalization of the parameters, hyperparameters, tuning, how the parameters are affecting. So you have to understand the maths behind all this, like a batch normalization, how the normalization of the data the data that is before giving it to the next layer, etc. So similarly, the dropout mechanism. Suppose if you like a dropout mainly used because to eliminate to overcome the problem of overfitting, because if you go back to the previous slide, that is this one, if you look at this slide and the complexity of how complex the model is, because here the 784 input pixels, that is an image, we 28 by 28 pixel image will be flattened, and then we have a one-dimensional 784 input pixel values, and respective, like suppose for each neuron, like suppose there are 784 neurons, for each neuron, like we have to calculate x1 w1 plus x2 w2, like, and so on, x784 or w784 plus bias. Okay, for each neuron we have to calculate this value, and then that will be given to the activation function. Like suppose if you are using the ReLU activation function, and we have to give it as a input to the ReLU activation function, so then it will produce a respective output. So if the network is more complex, so then what will happen? Why overfitting problem occurs? So I have already explained. So like suppose if the model is more complex, or all the neurons are active, or given importance, so then over a period the model will memorize the complete data and also the noise mainly. So because of that leads the model may overfit. So to avoid that problem, that is like suppose like every time, like so once you train the model for a number of epochs, and like the model will completely depends on a set of neurons. So if the model completely depends on set of neurons, so the model will expect to perform the 100% accurately or more accurately on the training data. It failed to perform the test data. So that to avoid that problem, so what we will do every epoch, and we will do the dropout. We like suppose here in this case 20% of neurons in a layer would be dropped out randomly, so that there is no possibility to like depend on a particular neuron or a set of neurons, because every time we are changing these neurons, so there is no such probability, so that we could overcome this overfitting problem. And another parameter, you can see hyperparameter, like a learning rate. So in this learning rate, we can because it is also going to affect the model performance, how we can apply this so that we can test, fine tune with the different learning rate values. So this is a simple logic, like a function defined like a scheduler, and it takes the two parameters like epoch and the learning rate. If epoch is less than 5, and the learning rate would remain the same, else the learning rate would be multiplied by 0.01. Okay, so and these are the functions or callbacks in the keras we use this schedulers, so that you can test. Like suppose here, let me run this code. I think okay, let us check it first. Okay, 20 epochs are set now, and validation test callbacks. So it is going to take because first 4 epochs there will be no change of learning rate, and after 5, that is from 5th and next, so it is going to update the learning rate, that is it is multiplied, it is reduced to 10x. Okay, so this is a simple how we can use this hyperparameters. Like in this lecture we mainly discussed about batch normalization and dropout mechanism and the learning rate. Okay, these are the 3 hyperparameters we discussed. Let us quickly summarize what we discussed before we move to the next lecture. So here I explained mainly this the basic part, that is data set. So like MNIST data set, handwritten digit data set, and the dimension 28 by 28. So the total number of pixels in that image is 28 by 28 times 28, so that 784 pixels. So we need to process each pixel, we need to have the neuron for each pixel. So input layer is going to have a 784 neurons, and then hidden layer, that is how complex we want to become our model you want. So based on that you would choose the number of layers and the activation function, number of hidden layers and number of neurons in the each hidden layer. So if the more number of neurons or more number of layers, then the model becomes more and complex. So because to do the all such kind of experiments, I would request you to have a strong background, like each and everything, like how a model and what is this dense, what are the dense layers, and what is sequential models, what are the activation functions, how the input, like, so if you could able to trace the value like which is given as input neuron in the input layer, and how the corresponding output from the output layer, then you will understand it, so that you can go for any like a kind of a research work or any such. So thank you for watching this video.